How many people do I have here? I have 1, 2, 3, 4, 5, 6, 7, 8, plus 1. Which means we're still missing 1. I don't know who that is, so let me try to figure that out. Is it Elijah? I haven't seen Elijah in a while. Hope Elijah's doing okay. Maybe I should take a note of that and find out what's going on with Elijah. Okay, so otherwise, Matt is in person. Everybody else is at home. I don't know. Is he supposed to be in class today? Question. I don't know. Look at this records here. Unit 6. Elijah would usually be in class today, right? Yeah. So he gets marked with that one. Everybody else is this one. Okay, and then submit. All right. All right, so I do have a new smartboard. I am happy about that. My smartboard was, the pen was really messed up for a while. There does seem to be something, it's like literally a brand new smartboard. There does seem to be something still a little off when it comes, and actually I'm not sure why there's so many black screens. Remember our, maybe not say our, but my, my goal for Q2 is to kind of step it up a little bit with AP students and the expectation level regarding the camera being on. So I also encourage you to use your own judgment. If there's something in particular going on at home that's maybe not something you want to broadcast, then I'd understand that. But generally speaking, students should have them on. If there is something that's a continual concern for you regarding that expectation, then you can email me and we can kind of have that conversation. But otherwise, I'd ask all of you to put your cameras on. I only see one student's camera. Good morning, Miles. Nice to see you. Good morning, Dorothy. Good morning, Julian. Good morning, Roland. Good to see you. Good morning, William. It brings like the human element back, It makes me remember that I'm actually teaching human beings. You're not some cyberbot just sitting in a black square. You're actually a human being. It's great. Thank you for doing that. All right. And you guys actually can't see me, which is the funniest part of that. You'll see me in a minute. I am going to be standing, as I was saying, working with my smartboard, which is brand new. There's still a weird thing with the as I erase something, it actually erases it and writes over it. Like I can't prevent it from doing that. So if I make mistakes until they figure that part out, and again, it's brand new. It's a brand new smartboard, but until they figure that out, I'm going to just be crossing things out if I make a mistake. The erasing is just all messed up. Besides that, I'm going to ask you to take some notes down right now. I'm going to teach you a new type of problem. Might be called a special problem. Again, the idea that there's special problems in physics and that the AP exam is all about, by the end of the year, it's pretty much how many special problems can you remember? It's really, really what the game is. Introductory physics, of course, is like a lot of the fundamental ideas and concepts, and there's for sure still fundamental ideas and concepts in AP physics. But when you take a good look at some of those AP exams, which by the way, you can do. You can visit the College Board website. You all have accounts, and you can search for previous exams, and they post them every year. They post the exam. I take some of that back. They don't post all the they don't post all the multiple choice questions. They do post all the free response questions. They keep the multiple choice questions private and secret and secured. But there's still a lot of practice exams available on their website. So when you take a good look at their exams in general, you realize that there's a lot of special problems, like the inclined plane and the pulley and the Atwood machine. And now we're going to do the sine, what I call the sine problem. So maybe make note of that, maybe like a separate page if you really, really into taking all down this information that I'm giving you to better prepare for the exam. Make a separate page in your notes, title it special problems, and that as I introduce a certain problem and say, this is one of those ones, you're going to need to know it, you can make a list of the names of those special problems so that maybe you can review those special problems either for exams or at the end of the year. Be my recommendation. The name of this special problem is the sine problem. That's at least what I call it. You'll see why in a moment. All right, let us begin. Where is my, there it is. Oh, this is all from the last class. Oh, and Matt, so sorry that you haven't seen anything because I've had this frozen. There we go. All right, let's just erase this. Oh, great. There it goes. Okay. 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 All right, the sine problem. In fact, that's not a very good name for it. I should rename it. Let's call it the hanging sine. That's more descriptive. Okay, so what is this hanging sine problem you mentioned, Mr. Kurtizak? This is it. Imagine that this is a ceiling and that we have some sort of hanging sine. Specifically, in a way that the sine hangs by two ropes as such. And these are, good old ropes. Oop. Not great. Yeah, I told you. It's new, but it's not great. It needs to be calibrated also, and those don't look like they're on the same angle, so that's already an issue. But I guess they're close enough. So now what we're going to do is we're going to put a dotted line down the middle. This will be called our reference line. Our reference line is just something we reference when we're measuring angles. And then what they usually do is they provide an angle from here to here and from here to here. And those are the same, so this is symmetric. So maybe let's make a note here that both halves of reference line are symmetric. So what I mean by that is whatever the angle is here, we can call this theta 1. This other angle, theta 2, is the same angle. And we'll call this, why not? We'll call it rope 1. And then, you guessed it, let's call this rope 2. Rope 1 and rope 2, attached to the sign that's hanging from the ceiling in a way that the ropes are not straight up and down ropes the way you wish they were. Would make this a lot easier of a problem, but they're angled. And this, of course, is your sign. The sign that says hi. We give the sign some mass, of course, and we don't know what the mass is, but we're just going to call it M. Has some mass. The typical question associated with this special problem is, what is the magnitude of the tension in both ropes? So how much tension is in rope 1 in newtons? Tension, again, is a force. It's a pulling force. It's never a pushing force, by the way. Ropes can't push. A rope is soft, right? A rope, when given the opportunity, just folds over itself and can create any shape you want. When you put it under tension, it's because you're pulling on a rope. And the rope will therefore pull back on you, because that's Newton's third law. When you pull on something, like the rope, it'll pull back on you with an equal amount of force, but in the opposite direction. But they can't push. Imagine attaching a rope to a wall, tying it to a wall, backing up, back, so it's all of a sudden nice and tight, and you're holding it sideways with this rope that's attached to the wall, and you're just holding the other end of it in the middle of the room. And then when you try to push the rope, what would happen? I mean, it would just start to become loose instantly. As soon as you get closer to the wall, it instantly starts to droop and the tension is lost, right? Ropes can't push. Ropes can only pull. If they were solid and they were rigid, like frozen ropes that like don't bend, and they're like so cold outside that they were like solid, stiff ropes, then it's more taking on the properties of like a pole or a piece of wood. And then yeah, it can push or pull. But ropes that are at normal temperature, that aren't frozen solid, they can't push. They're not pushers. They're just pullers. Just pointing that out. And so the amount of pulling force in these ropes, which we're going to call FT1, and we're going to call this one FT2, are under question. Since there is symmetry and theta1 is equal to theta2, you should know that the tension in magnitude, just total amount of tension in rope 1, is equal to the total amount of tension in rope 2. Those are two important points. Since they're symmetric, there should be no properties of the right side of the reference line that are any different than properties of the left side. That's what symmetry means, and I'm saying that it's quite literally all things. It's not just the angle, it's the tension too. There's nothing really different about either sides than they have to have the same tension, they have to have the same angle. That's the problem. How do we visualize it? And then, of course, after we think about how do we visualize it, and I show you how to visualize it, then the question is, so how do we do it? So let's go down that process of thinking. I'm going to pull up, my vector addition Yeah, these don't get bigger, unfortunately. I can zoom in for you, Matt, a little bit. That's a little smaller for you. Let's see if we can zoom in for Matt. There you go. Okay. So now what I'd like to do is, if possible, bear with me here. I would like to change over to a different mode. Excuse me, to annotation mode. I should be able to draw right on there now. So this vector here is going to represent the tension in one of the ropes. I guess it's rope 2. And this vector over here is going to represent the tension in rope 1. And you know, maybe I could have redrawn it. Now that I think about it, usually they don't show it with the ropes attached on the ends, although it's still the same problem. I'm just now realizing that usually when you see this printed in text, they show the ropes coming together attached to the middle. but it doesn't matter. But those two vectors will represent the tension. Just seeing, did I make those the same? I think so. And let's see the components of those tension forces. Those don't look quite, I don't know why. B looks a little different to me. Why does B look different? There. Maybe that's, something was off. Okay. So let's draw in our sine. I hope it works. Let's see. Ooh, it does. So here's our sine with a mass of m. And these are now, again, tension vectors. Oh, see? So what I'm drawing is not coming through on your screen. This happened to me in the other class. So I just drew stuff on the screen. Matt can see it. You guys at home cannot see it. And I don't fully understand it, so just bear with me here. With my old one, my old smartboard, this would be coming through your screen. Why is it not coming through? Maybe I have to go back to this like that. Still not coming through. Bear with me here. It doesn't work. Interactive mode. Look at PC interactive mode. I'll click here. Oh, now it's on your screen. I don't know. Yeah, I don't know why it does that. It's very strange to me. All right, trying again. Now, when I draw this, you at home should see sine. Yeah. So there's our sine. Here's our, oh, so what I had written before was that these are tension vectors. That represent the amount of tension in each of those ropes. Usually we label them, again, Ft for tension. I'll label this one 2. This was a 2. I'm not sure why that doesn't look like a 2. Magnitude of F2 would be, yeah, that's not good, so sorry. And that becomes the issue. Now we're going to see that when I try to erase, the eraser doesn't work. Try it again. If I try to erase this, it's going to draw over it as it erases. See that? Isn't that wonderful? Yeah, that makes a lot of sense. Yep, so I can't, all right. I just can't make any mistakes. All right, try again. Sorry, bear with me. Okay, do this again. This, I'll draw it up here, would be, oh, it's still under the eraser. Okay, or no, that's again, FT2. So that's the tension in rope 2. This one over here would be the tension in rope 1. We would usually write FT again for tension, rope 1 to indicate rope 1. Now, usually I wanted to point out that usually in the way they present it in their physics, way they type these problems up, usually the angle they show is the angle in here. And you have to be aware of that because when you're looking at a vector diagram the way I've drawn it, my triangles don't include that angle. Like it's not inside, that angle is not inside the triangle. Right? So you would potentially have to think about that. Unless maybe there's another way. Give me 1 second. Unless there's a separate way of, yeah. 1 second. Yeah, I don't like that way of representing it. Yeah, we could do that. All right. I mean, we can view it that way. That's fine. So just be aware of that. Just be aware that when you draw this vector triangle, just be careful with the angle. Just know that in the way that they usually draw it in a textbook, the angle is always shown here, almost always. Like now I have it that way. Okay, and so now, I don't know if I lost this. Go there. There's the mass. So now what we have to do is think, if this is in equilibrium, what's called equilibrium means that all of the forces are balanced, balance of forces. Another main idea, sine is in, and actually we call it static equilibrium. Static means stationary, not moving, which means it's at rest, balanced forces. That's different than something we'll talk about later, which is called dynamic equilibrium. That's like a car driving at a constant speed on the highway. If the car is moving at a constant speed, not accelerating, the forces are still balanced. That means the forward force is still balanced with all backward forces, and all upward forces from the road are balanced with the weight. But when the car is actually moving with a constant speed, like I've just described, not accelerating, but it's moving, we'd still call it equilibrium because it's still a balance of forces, but we call it dynamic equilibrium. Dynamic because motion is involved. Position dynamic usually means something is changing. In this case, your position is changing, so we call it dynamic equilibrium. Static equilibrium, again, it means the thing is at rest, not moving, that forces are balanced. So now what we want to do is think, what are the forces? What are the forces that we're talking about? We know that gravity is pulling down on this. With a force equal to mg. That tells us there must be two other forces in the, well, there must be other forces in the upward direction to cancel out with that downward force known as its weight. Otherwise, it would be hanging. If it's hanging again, that means the total upward forces and the total downward forces must be equal to each other, but opposite in direction. I'm just trying to think about whether, I don't love, to be honest, over all the years, I don't usually do it that way. I usually show it the other way. Usually like to show it like this. I just think it makes more sense. Makes more sense to show it like this. It's fine. I'm going to stick with it like this. This is the way I like to do it. So just be aware that there's that issue of how you view it with the angle. If that's the case, just know that that angle is, oops, do that. If you are viewing it in this way, this is this way I like it. I don't know why, I like it. That angle is this angle over here. Those angles are equal, right? Those are equal angles. I don't know, what's it called? Interior opposite or something along those lines. Opposite interior angles. I don't really know. I don't really care actually what's called. I just know that they're equal. And so with that in mind, just be aware of that. I like looking at it this way because I see that there's an upward force. It's very easy for me to see this upward force. And it's also very easy for me to see this upward force on this side. And those are the y components of this tension force. So I can write Fy on both sides if I want, just to represent that that's a y component force, the vertical force, which we call y along the y-axis. And those two forces that I just wrote, Fy's, must add up to mg, right? They have to. Whatever they combine together to create in terms of a total force, this Fy on the left side and Fy on the right side, Fy1 plus Fy2, those two, and together they are in the same direction, so there must be a plus sign between them. They're both up. So we call this plus. Up is usually plus, not always, but whatever you choose. I'm going to choose that as plus. Then Fy1 plus Fy2 since they're again in the same direction on the same team, their efforts are combined, right? They're as an additive effect, so it makes sense to have a plus sign between them. Have to be equal to what? Have to be equal to mg. So mg is the total amount of downward force. Think of it as one team trying to yank the thing down. The other team is composed of two people, Fy1 and Fy2. They're both pulling up, but we remember that they're both pulling up with equal amounts of force, right? That's an important idea. So when I said before Ft1 equals Ft2 in magnitude, that means the y components are equal. Fty1 equals Fty2. Again, Ft just stands for tension force. Y means in the vertical direction. And it just means that the y, I'll put a 1 here, I guess, to indicate that's Fy1. This was Fy2. Those two y component forces are equal. What does that physically it just means that if the vertical force lifting from rope 1 on the left is 20 newtons, then on the right, the rope that's on the right also has a y component force of 20 newtons. So they're the same. So since these are the same, this one and this one, then it's really just two of those things, right? Something plus something that's the same is two of those things. One apple plus one apple is two apples. They don't look like apples. They look like different things, but I'm just trying to convince you that they're the same because of the symmetry. Because of the symmetry. So what we end up with is 2 times that y component force, right? 2 times of it, one here and one here, is equal to mg. So this is worth recognizing that it has to be a true statement. 2 times whatever the y component force must be equal to the weight. So what we end up having to do is, we end up having to do a system of equations. This isn't the answer. This is just how we go about finding the answer. We have to do a system of equations. One of the equations is on the referencing the vertical forces. So I'll mention that here. This is a vertical equation because it references the vertical forces. And then we have to do the same thing for the horizontal forces. So unfortunately, I have to erase all of this at this point because I'm out of space. In fact, I'm not out of space. It just looks like I'm out of space. And it looks like that because I've zoomed in for Matt in class. If I zoom out, look at that, Matt. There's a lot more space up there. Need more of that space. So let's just put some numbers in there just so it makes more sense. This might make some more sense to you. Let's just say that the mass was, I don't know, 20 kilograms. And G is 10. So I can write that up here. Let's just say that the mass was 20 kilograms. Then how much does this weigh? 20 times 10 will be a 200 Newton. It weighs 200 newtons. If it weighs 200 newtons, how much tension do you think is in Fy1 and how much tension is in Fy2? I didn't say Ft, like the magnitude of the tension. We're just looking at the vertical forces again. If I know that the downward total force is 20 times 10, which is 200 newtons, how much force do we think is in the vertical component of the first rope, and how much force do we think is in the vertical component of the second rope, knowing they have to be the same number and they have to add up to 200? Anybody at all? What two numbers are equal to each other but add up to 200? Anybody at all?
100.
100, yep. So we know that 100 newtons must be in that. This must be 100. So I'm just teaching it to you right now just with some numbers because it starts to, I think, make a little bit more sense when you think about the numbers. And that means the other one is also 100 newtons. We don't know what the actual tension in the rope is yet. Those are the diagonal vectors. But we know that because 200 newtons is the weight, and therefore that weight, called the load, usually in engineering we call that the load, is divvied up over two different things that are absorbing that load. And since they're absorbing the load equally, it must be 100 in each. Now, let's just say we were given an angle. Let's just say, in this problem, which I didn't do, let's say the angle that they gave us was, of course, it's not some random angle. It's either usually 30 degrees or 45 degrees or 60 degrees. 99% of the time, it's one of those three. I've drawn them as if they're 45 degrees, so let's stick with that. If that were the case, then this here is a 45-degree angle. Right? And the one that they would have labeled would have also been 45. Those would have all been 45, right? So now the point is that I only can figure out how much tension is in this rope, which represents the actual tension. I'll put the word actual tension, like what you'd feel if you went over to the rope and actually just felt it with your hands. Like that amount of tension is numerically represented as the hypotenuse that I just pointed to. We can only figure out that hypotenuse if we know the vertical component, which we know is 100, and we need to know the horizontal component too. Because if we know the horizontal and the vertical, then we should be able to just use Pythagorean theorem to figure out what the hypotenuse is, and the hypotenuse would represent the actual tension in the rope, right? So I am going to actually delete because this need to start fresh, clean spot. Right on. So I'm going to delete that if you don't mind. There you go. So now I know that this was, again, 100 newtons. An example, this was 100 newtons. This was 200 newtons because we said the box had a mass of 20 kilograms. And we've said that this angle is 45 degrees because, again, the reference angle, let's just say that they gave us was 45 degrees. So if that's true, we can just select one of these triangles and just kind of expand it a little bit to see it a little more closely. And think, all right, if this number is the number 100, and this is the angle of 45 degrees, how can I work out what FTX is? The X component force. That's the amount of force that's yanking this thing to the left. Like if the rope literally goes on an angle like that, the rope is effectively providing a lifting force, which is the FTY part. That's what's providing the lifting force and absorbing some of the weight. But the X component force is literally trying to yank it to the left. That's what FTX is doing. And we want to know what that number is because if we know what the vertical piece is and we know what this piece is, then we could easily just work out the actual tension, FT1. So how would we do that? Well, it comes back to geometry, right? This would be really opposite. FTX is really adjacent. We can't use sine or cosine because sine or cosine has hypotenuse in it, and we don't know what the hypotenuse is. The hypotenuse is the actual tension in the rope. That's actually what we're trying to solve for. We certainly don't know that yet. So if we picked up those three tools, we'd have to put those two back and say sine and cosine wouldn't work. Tan would work, right? Tangent would work. Tangent of an angle of this angle, this 45-degree angle, but tangent in general is, again, opposite over adjacent, right? So in this problem, you'd say, well, we've got in this problem a 45-degree angle. The opposite is really this number here, 100 newtons, divided by this adjacent piece, which is what we're calling FTX. So let's just write it as FTX. Let's cross multiply because our goal, again, is to solve for the numerical value of FTX, knowing that we'll then have a numerical value for the X piece, the Y piece, Pythagorean theorem, done. FTX and FTY would then be known. So let's do that. If I cross multiply, I'd end up with FTX times tan 45 equals, and then cross multiplying the other way is just 100 times 1, which of course is just 100. And then to get the X component, I'd have to divide out my tan 45. 100 divided by tan 45. Remember that tan of 45 is just a number. Some students sometimes are like, how do I treat that thing again? What is it? Is it like it's just a number? It's like, again, it's technically 1, right? It's technically opposite over adjacent for a 45, 45, 90 triangle. It's 1 over 1. But it's just a number, tan of anything. It's either a decimal or it's a number usually. Well, tangent actually could be a number greater than 1. But cosines and sines are just decimals. Either way, they're all just numbers. So you just treat them like they're numbers. You just divide it over like it's a number. All right, 100 divided by tan 45, what would I get? 100 divided by, I'm just typing it in, tan 45. Oh yeah, I just said that it was 1, right? I forgot. I don't know why I bothered typing that in. It was because I just said tan 45 was just 1, so it's just 100 newtons. Since I picked this 45-degree angle, the vertical piece, as a problem that involved a 45-degree angle, the vertical amount of force is equal to the horizontal amount of force, because that's the property of any 45, 45, 90 triangle, right? Whatever the amount is on one leg, it's the same amount on the other leg, so 1 to 1. So since we already knew that the vertical piece was 100, all the horizontal piece would be 100. If you knew that in a test, you could just go with that, not even waste time figuring it out. But if it wasn't a 45-degree angle, like a 60-degree angle, you would have had to do the work I just did here to figure that out, what that actual number was. So now I'm going to erase this, finish the problem off. That doesn't necessarily mean that we're done with the problem once that happens. It's because I want you to remember that sometimes their problems aren't all numerical. Sometimes it's just algebra. So we'll return to that algebra view in just a moment. So my point was, if this is now 100 newtons, this is 100 newtons, and what would this amount be? This is just, our typical c squared equals a squared plus b squared. Little did Pythagoreans know, I'm sure, how much his Pythagorean theorem would be used. I'm sure he didn't know that it would be used in all of science and all of engineering for all vector math. Sure, he just thought it was just had to do with triangles, and that was kind of one of those cool things he discovered with triangles. It actually ends up being extremely important and useful for all areas of science. Not all areas, but certainly all areas of physics and engineering. So anyways, we're just square rooting it, right? This would just be 100 squared plus 100 squared square rooted. So what do we get when we do that? 100 times 100 is 10,000, right? Because it's 4 zeros. 100 times 100 is 4 zeros, so it's 1 with 4 is 10,000. So I guess it's 10,000 plus 10,000, which is the square root of 20,000. I get 141.42 newtons. This is the amount of tension, the actual tension that you actually would feel in the rope, in both ropes. Now let's compare it to the weight. How much did this thing weigh? It weighed 200 newtons. So does the tension in each of the ropes, do they even have a tension that's the weight? You'd say, oh, it's interesting. No, it's actually this amount of tension that's acting in this direction, 141 point, whatever we said, 42 newtons, is actually less than what it weighs. Actually less than what it weighs. All that really matters is that the vertical components, like 100 over here and 100 on the other side, add up to 200. And as long as they give you problems like this that have symmetry, and usually they do, that's an easy thing to recognize, that the y components would be equal on each side and they would absorb half of the weight. What do you think would happen if, I'm going to delete this now, if this angle were to change? What if it was the same block, the same weight, but now they have it tied like this? And this is now gets down to the conceptual questions, which can be very difficult in an AP exam. And they say, comparing the first situation to this situation, the first situation, what I just worked out, and then they show another image compared to this situation, and they'd say, and it's the same block, it's the same mass, whatever it was. Said it was 20 kilograms. Still got two ropes, and it's still tied up. In which situation do we think there would be more tension in the ropes? Do we think there would be more tension in scenario B, which we're looking at now, or do we think there would be more tension in scenario A, which was the one we just worked out, where it was a tension of 141? Any thoughts? Any guesses?
Would it be more
In which one?
on the one on the screen?
Yes, it is more on the one that's on the screen. Absolutely. So I want to have you think of one thing, which is a good visual, I think, which is a gymnastic image, which is the rings. There it is. This guy on the right. Do you know how much tension is in his muscles right now? Do you know how hard this is? Do you have any idea how hard this one is here on the right? The amount of force and strength required to do that is phenomenal. If someone asked, which is more difficult, doing what he's doing there or doing just a regular hang, like this guy right here that's just hanging? Assuming it's the same person. Let's say this person can either be in this position on the right of the screen or he can be just straight hanging down. Which one would have more tension in his muscles? Everybody would agree, of course, the one on the right, right? Because in this case here, the hanging case, each of your arms end up having half of your weight. Half of your weight. So in the hanging case, if remember I had that example where the sign was 200 newtons, and this guy that has a blue shirt on that's just hanging, he'd have 100 newtons of tension in his muscles in his left arm and 100 newtons of tension in his right arm, and those would be upward forces pulling on his shoulder. However, remember that when we just did that problem, which was 45 degrees, how much tension was in the ropes? 100 or more than 100? More than 100. It came out as 141. Right, because that was a root 2 scenario. Root 2 is 1.41. So the point is, as soon as that angle, as soon as you go from a position like this and go like this, now you're actually producing far more tension inside your muscles. And the reason is because, going back to our image over here, sorry, back to, where was I? The reason is because as that angle goes down, a lot of your actual tension ends up going into the horizontal pieces, which these horizontal pieces don't absorb any weight. The amount of force that's leftward, the leftward horizontal component, are equal in both ropes, right? If I'm looking at these, oops, sorry, I mean to do that. If I'm looking at the horizontal pieces on both sides, they're equal. Right? If this one was 100 newtons and this was 100 newtons, these cancel. Right? These are full cancellation. That's why the sign doesn't go to the right, sign doesn't go to the left. It's just a cancellation that stays in place. But my point is that as the person starts to go up onto that angle like this, more of their tension becomes horizontal. Because you can see that as I vary this vector more vertical, it has more vertical force and less horizontal. When he goes like this, now more of the force is actually horizontal, which means this vertical piece still has to absorb half of your weight. And so does this vertical piece. It still has to absorb half of your weight. Well, visually, we saw it got smaller, but it can't get smaller. It still has to be 100 newtons, which means this hypotenuse would have to get much longer so that this value is still 100 newtons, which means the amount of tension at that angle is really far more tension to maintain 100 newtons here and 100 newtons here to compensate for that. So that's the image that I always try to have my students remember. That gymnast example, when they give you scenarios like that are conceptual questions, scenarios where there's more of an angle like this always has more tension than the scenario where it's just straight up and down. Okay, and then lastly, I wanted to do one other thing, and then we'll move on to the homework assignment questions. Had you needed to do that, and you used, let's just say you used this angle, had you needed to do an algebraic, more algebraic, just remember that this one right here would be mg divided by 2, right? And this one over here would be mg divided by 2. It's just a weight. Remember, just mg is just a weight. So half of the weight has to be in one vertical component, and then half of the weight has to be in the other vertical component. And then whatever FT is, these have the same tension in both. Just know that this ends up being the formula that would represent this would be FT cos theta. That's that amount of force. And they would again add to 0. This would be considered a minus if you want to think of it that way. This is a plus, minus because it's a leftward, plus because it's a rightward. If you technically needed to jam that all into the Pythagorean theorem, you could. I don't know that they would force you to, but maybe. Sometimes they ask for crazy formulas. If you had to do that, then it would be mg, well, before I write that, it would be, in general, the magnitude of the tension would be the square root of whatever the x component tension is squared, plus whatever the y component tension is squared. That's just c squared equals a squared plus b squared square rooted. So ft, yeah, so sorry that I did that. I just flipped them, and I can't erase. I'm not going to try to write all this over. But I'm just pointing out that I'm putting this one over here. This one would be mg over 2 squared plus, and this one would be, in fact, I don't even know if it's worth doing this, because then you'd have to, yeah, I don't think they would have to, because you'd have ft on both sides. I don't think they'd have you try to force it in, and you have to try to square everything and factor it out. So I don't think it's necessary to actually know this part. So I don't think they would ever have that. But this they would know. This they would ask. They'd ask, what are the equations that model like the y component force? It's always half of the weight. What is the equation that models the horizontal component force of the tension? It's ft cos theta. All right. At least I exposed you to that one special problem. I'm going to now open up the class to you guys to work on some of the problems that are from homework assignment. I'm going to just direct you again to, well, let me delete this first, erase this. To Google Classroom. Matt, you can take out your Chromebook. Everybody else is already at home. You can go to Google Classroom. Close this out. You'll see that I posted on the stream a bunch of images, since there was 19 questions. Just pointing out that the first post says AP 7.2, AP 18.2, AP 16.2. So question 7, question 16, and question 18 were long in terms of physically long. You had to scroll because on all 3 of those questions there were graphs. And when I first screenshotted it using like an extension, I didn't do like a box capture. I just said capture the whole page. And then when I looked back, I saw it had missed capturing like part C and part D. So the reason that those are there, these extra 3 are the bottom of each of the problems. Of part 7, number 7, bottom of 18, bottom of 16. And all 3 of those, I think, C and D were missing from the original ones that are in the list. Other than that, the rest of them are all captured well enough. So what I'm going to do is ask you guys maybe to go over some of the problems that you may want to talk about. I'm going to actually just mention a couple that I think you should review as a class. The free response we can do on another day. In fact, I'll leave it to the groups. You guys can just have that conversation with each other and just say, hey, do you want to mention, talk about group problem 1, problem 2, and then just stop and talk about the ones that you think are worth your time to talk about as a group. And then we'll come back a little later. Whether there's time for me to talk about them today or not, I don't know. I might end up just recording myself, reviewing these questions and posting it and saying, to save class time, you can watch these on your own. That's probably what I'll do. But for now, we'll do the breakout rooms. All right, so here we go. Breakout rooms. Set up breakout rooms. All right. So again, just go through those problems. They're already posted there. I would encourage one person in the group to maybe present the screen again and say, okay, if you say, hey, do you want to talk about number 1? And everybody's like, what's number 1? And it becomes confusing again, right? So somebody should take that role, present it, say, okay, let's look at this number 1, this one that he has as number 1. You want to talk about this one? No? Okay, move on to the next one. And so everybody should be able to see that. my request. All right, I'll be popping in on you a little bit. What is it? Oh, you're not in yet. I got you. I'll toss you in. All right, it should be throwing you in there in a second. Okay, I'm gonna wait another second for everybody else to come back in. I'd like to use the last 15 minutes or so to just go over some of them myself, if I could. All right, you're all back. All right, I'm gonna present my screen. I'd like to just step you through some of these. And again, I apologize that, I'm trying to learn what the best method for using AP Classroom is. In the future, I would probably say write down your answers, because I know that that's already not a great thing. You're like, what did I put? I don't remember, and I understand. So in the future, I would say I probably won't scramble them. I'll tell you to write down your answers so that when we review them, you at least have the same order as everybody else. You know what you put down for your answer. So apologies for that. All right, live and learn. Let's go over to the questions. For one, it says a 2 kilogram block starting from rest slides down some length, 20 meters, dropping a distance of 10 meters. The speed of the block. So really you need to know the acceleration first, right, for this problem. Oh, so sorry, Matt. I don't know where you're looking, Matt, but there we go. So the acceleration down a frictionless, if it's frictionless, and it does say frictionless, is g sine theta. G sine theta is something you should just store to memory. Fraction of g. It's not g cos theta, it's g sine theta, because if the angle of the ramp is 0, it's like that becomes a 0-degree ramp, is just a flat floor. Then what would the sideways acceleration be? Be none. That's why you have to use the sine function, because sine of 0 gives you 0, and you'd say that makes sense because there's no gravity doesn't pull you sideways. If you lowered this plank down to 0 degrees, there'd be no acceleration sideways. So it's a sine function, g sine theta. So you'd have to do g sine of whatever the angle was. Since you don't know the angle, you'd end up having to work it out, right? So you'd end up having to do it looks like they gave us a vertical component and a hypotenuse. That would be an opposite and a hypotenuse. That's a sine function. So you'd end up having to do the inverse sine of opposite over hypotenuse. Inverse sine of 10 over 20, which we know is a half. That gives me an angle of 30 degrees. So the first step is figuring out what that angle is, 30-degree angle. Then when to figure out the acceleration, it would be g sine 30, g sine theta, right? 10 sine 30, which again, we know is a half. So the acceleration down this ramp is 5 meters per second squared. Now we can tackle the question, which is what is the speed at the bottom of the block? There's no bottom of the ramp. There's no mention of time at all. So we can use the v final squared equals v initial squared plus 2a delta x. Let me just see if I can, my in, shoot. Give me a second. Is it coming through on your screen? Yeah. So in that case, we would use v final squared equals v initial squared plus 2a delta x plus, right? I don't know what's going on with that. V initial would be 0 because it starts at rest. And so our final speed would be the square root of 2 times the acceleration we got was g sine 30 or 10 sine 30, which we knew was a half. I'm sorry, which was 5. And then the length of the ramp was 20. So it looks like 20 times 5 is 100, times 2 is 200, so root 200. So it's 50 root, I don't know, 2 root 2, I don't know what it is, but you can work out, I guess you'd have to just plug it in. Root 200, I get 14. Notice it's an approximation. It does say is most nearly, so I get 14.14 meters per second. All right, the next question would be, so a lot of, multiple steps there. Next question is here, sorry. Next question was number 2. I'm gonna, the magnitude of the net force here. Well, remember, if the acceleration down the ramp is g sine theta, the acceleration is g sine theta down the ramp. And we know that in general, when you take an acceleration and multiply it by a mass, that turns into a force. So I really just have to multiply this side by m and this side by m, right? Because ma is now a force. That's one way of recognizing that the force that's pulling it down the ramp is mg sine theta, right? G sine theta is the acceleration. So if they've given us a 2 kilogram mass, G is 10, I'm assuming it's the same length, so we knew it was a 30-degree angle, which is a half. Then 20 times a half is 10 newtons. Okay, moving on to the next one. Try to clear that. Back to this. Move that away. Here. Okay, next one as a free response. I'm going to give you all the answers to those. Another day. This one says an object of 10 kilogram mass is released from a planet and goes into free fall. Based on just this information, what is the force due to gravity exerted on that object, which is called the weight? Force due to gravity is just the weight. Since this is a speed versus time graph, we know that the slope of this graph represents acceleration, right? Acceleration is the slope. Acceleration is the rate of change. Right? So if I can figure out the slope, which I might as well pick this point here and this point here, because all these other ones would be guesswork. These aren't going through nice spots that I could easily read, but at the end I can, right? Then I know then that triangle is showing that there's a 20 meter per second speed increase in how long? In 6 seconds. So the change in speed since it was dropped from rest, meaning started with no speed, of course, would be 20 over 6. What is 20 over 6? Don't know. 20 divided by 6, I get 3.33. So that tells me the acceleration is that. And if they're asking for the force of gravity, which is the weight, mg is the weight, and they've given us that it's a 10 kilogram mass, then the closest amount would be 33.3, but I guess it comes out as 35 newtons, roughly is how much it weighs. All right, moving on to the next one. Again, next question. Next question, here we go. A vehicle lands on Mars and explores its surface. The average gravitational field on the surface. So when they say average gravitational field, they're just talking about G. G can be expressed in units of newtons. I don't know if it's supposed to be a divide. There's this mistake there. It's supposed to be newtons per kilogram. Don't worry about the units. They're referencing G. It can be either meters per second squared or newtons per kilogram. The weight of the vehicle is defined as the gravitational force exerted on it by planet's gravity. Which of the following statements is true? So this one did include some information that I didn't really review with you yet, but the idea that when you get closer to a planet, the gravity gets stronger. When you get further away from a planet, the gravity of that planet gets less and weakens. Since your weight, how much you weigh, depends on how much the planet pulls on you, as a spaceship actually approaches a planet from outside far away, the weight of the ship actually starts to increase, meaning that the planet starts to pull on that spaceship harder and harder, which is called weight. Not the mass changing. The mass of the spaceship is the same, but the weight begins to change. So the weight increases as it approaches the ship. That's why B is one of the correct answers. The vehicle's weight increases while descending to the surface of Mars, since while it gets closer to the planet, like a magnet getting closer to another magnet produces more force. Same thing with any other object getting closer to a planet. The pulling force between them gets stronger. So B is one of the correct choices. And so is D. Since Mars has less gravity, the vehicle won't weigh as much on Mars as it will on Earth, because remember, weight is m times g. Mars has less gravity, the value for g is less there, the weight would be less there. So it's B and D. Free response. This question is assessing the student's understanding of Newton's second law, which we did the Pivot Interactive Lab, and we determined that the acceleration was directly proportional to the net force, right? The acceleration of the system is in direct proportion to the net force. Which graph represents direct proportion? Choice A. Correct answer is A, because that's a direct proportion graph. Next. This question shows some block being pulled with a scale that measures how much force it's pulling with, and they tell us that it's pulling with 32 newtons. Oh, God, it drives me nuts. I hate having to do this. So they say that the force pulling it this way is 32 newtons. We know that the weight and the normal force cancel in that case. They're not of interest. So the net force, the unbalanced of force, is this. It says there's no friction, notice. It says friction between the block and the surface is negligible. So that means there's no other forces to consider. So that means if they're asking us for the acceleration, we know it's the net force divided by the mass. The net force would be 32. Careful here, most students would like to grab the number 80 and plug it in right here. Cannot do. That is the weight of the block, 80 newtons. M is not the weight of the block, M is the mass of the block. So on the side, I'd have to say, all right, mg, the weight of the block is 80 newtons, that's what they told us. Therefore, m is this divided by 10, right? When you divide both sides by g, the mass of this is actually an 8 kilogram block. So now when I plug in 8 here, 8, 16, 24, 32, I get 4. Careful with mixing up weight and mass. That can happen very easily. Be aware of that. Moving on to the next one. You know, there's only a couple minutes left, and I'm going to record answers to these as well, so you guys can view them also. This is one of probably the hardest ones. So this one, you just have to remember, if there's tension pulling it on this angle, oh, God, it happens every time. If there's a tension pulling it on this angle, there's a y component, and there's an x component, right? And so the idea is that these forces, let's say that, I wish I could erase that. The normal force, which is up, plus Ty, which is right here, those are two upward forces that come together, so ignore my cross out there. Those are working together, have to be equal to mg. Just like the sine problem, right? All upward forces have to equal all downward forces since it's not moving up nor down, it's just moving sideways. And so then you have your frictional force as well. And so this is a challenging problem because first you have to figure out what the normal force is, Fn, using this formula. So you see that it would be mg on this side minus Ty, right? And that makes sense because if there's nothing pulling up, Ty would be 0 and the normal force is just mg. But as soon as something starts pulling up on it a little bit, it lifts that object off the surface, reducing the pressure underneath. So the normal force is not the weight anymore, it's the weight minus how much it's lifting. And that was needed because we needed to know the frictional force. Remember that the frictional force is mu times the normal force. So when we plug that in, mu, the normal force has to now go in as mg minus, it's this piece here, mg minus Ty. So this is an expression for the friction force. And that sets us up now for doing the acceleration, which remember is always the net force divided by the mass. And the net force would have to be Tx, which is pulling it to the right, minus the friction force, which is pulling it to the left, right? Because it's accelerating in the sideways direction. This is a horizontal acceleration. What is the expression for Tx? It would be T cos theta, because it's adjacent to the angle. There's a lot of pieces there. So that means the acceleration would be Tx, which is pulling it to the right, which is T cos theta, Tx, minus the friction force back in the back other direction, which I've almost run out of space, but this would be the mu mg minus Ty, instead of writing it all out. I believe it's this one here, T cos theta, yeah. Mu mg minus Ty. Yeah, so it would have been D. It kind of ran out of time because we're being excused. So anyways, that was a challenging question. I will say that I did peek at people to see how they did. The vast majority of students did phenomenally well on that assignment. The vast majority of students got between 2 and 3 questions wrong, which is superb. That's out of 19 questions. And I actually subtract away the free response questions. It might have been out of 16 or whatever. But most students got somewhere around 13 to 14 correct. So I'm going to send you a message, everybody a message that kind of just indicates where I think you're at, saying, great job, you're doing great, keep going, or you might want to consider coming in for some extra help. And they'll just kind of indicate when I'm available after school if it seems like you might be kind of needing some extra help on this topic. But generally speaking, the class did extraordinarily well on that assignment. I'm going to, we'll see you later, Matt. I am going to record a full review of these problems, and I'll post it to you sometime today. I'll probably be recording it during my break. Let me just bounce back to here to actually see you one more time. Un momento. Por favor. Here you are. Okay. So any questions from anybody? No? All righty. See you guys later. I'll be keep your eye on Google Classroom. I might post something there other than that video. So just stay tuned. See you guys later. Have a good day. Bye-bye. One second. All right, what's up? Okay. Okay. And what is your name again? Oh, Patel. Okay. You're referring to like the assignments or the quiz or both? You want to just go back and look? I'll go back and look. I'll update your grade. I'll do it now. All right.